By the way, in case you've just joined us, please just log on to www.chatterban.com and study with us. After watching this video here, after taking some of your notes there, please try out the examples before. You can pause the video and then check afterwards. Pause the video, you can replay in case there's something that is not okay. In case of anything as well, you can always write a comment in this at the bottom of this lesson here. There's a comment section, so you can just write a comment and your friends, even the teacher, will be responding to you. Attempt the quiz and check yourself about the progress. Please invite your friends as well to join us. So, after having looked at how the adjustments of the spectrometer are done, let's now turn to using of the spectrometer to measure the refracting angle of the prism. On this one here, what we do is very simple. Simply make sure that the collimator light, the beam, remember that the collimator produces parallel beam. So the parallel beam coming from the collimator is directed onto the prism in such a way that the apex, where we have the refracting angle of the prism, is facing that light. That should be the first step. So once that one has been achieved, then you just need to make sure that you move the telescope T1 either to or away until when light from the collimator hitting one face of the prism is reflected and is seen on the cross wires of the telescope. So once that one has been done, then you simply need to measure and record the telescope position as theta naught. Then you turn the telescope to the other side as well until when a beam of light is focused. The image of the slit of the collimator, remember the collimator slit is just the hole. A slit is just a hole. So you have the source of light this other side, and the light is coming from that point there, and then it is produced as a parallel beam like that. So once it is at position T2, after seeing the image of the slit clearly, read and record the new position of the telescope as theta 1. Then get the difference between these two readings and read it as your diagram, as your angle, theta being equal to theta 1 minus theta naught. So once you have got this, then the angle of the prism A is simply got from theta out of 2. We're going to see the theory behind this experiment here shortly. So in other words, this is what we do. The first step, the prism table is turned so that the refracting angle of the prism faces the collimator. The telescope is turned to position T1 to receive the light reflected by the refracting surface XY. Then, after that, then adjust the telescope so that the image of the slit is observed at the center of the cross fields. So, after that, then you simply read and record the telescope position as theta 1 on the turntable. Then do the same for the other side, XZ. Read and record the new angle theta 2 from the scalar scale of the spectrometer. Then afterwards, the angle between the two positions of the telescope theta is got from theta 2 minus theta 1. And our refracting angle A of the prism is calculated from this expression here. So that is the experiment in brief. But then, how do we come to this equation here? Remember, if you're describing an experiment, the theory of the experiment is not needed, but we need to know where it comes from. You may be given questions relating to the refracting angle of the prism and then that angle theta. So we need to know where it is coming from. So in case the telescope is moved to position T2 to receive the light reflected from the reflecting surface XZ of the prism, this is how it looks like. In other words, look at this. This is the parallel light from the collimator. It means that line 1, 2, and 3 are parallel lines. And what do we know about parallel lines? Is that when you draw a line cutting through each of them, this angle here is the same as this angle, vertically opposite. At the same time, this angle here is the same as this angle. alternating angles. So which means therefore that if the light comes from this other side and then strikes the refracting surface of the prism, remember this is reflection. So the angle I here is equal to the angle R. Angle of incidence is equal to angle of reflection R. Meaning that this glancing angle alpha is the same as this glancing angle alpha. So since this glancing angle is, in case I just continue and see where it is coming from, this angle here and this angle here are vertically opposite. Which means therefore that this angle here is equal to 2 alpha. Now this is on one side of the refracting surface, which means that even the other side it will be the same scenario. So you have 2 beta. So in case you look at this, from what I've just said here, if this angle here is the same as this, then it implies that this angle here is going to be the same as that. Likewise, 2 alpha, this angle here will be the same as this angle here. So, after having seen that this is our refracting angle of the prism, that our A is equal to alpha plus the beta, and we know that our angle theta is the angle between the 2 telescope positions, then this angle alpha, this angle theta is given by 2 alpha plus 2 beta from geometry, from what we just done seen there, and this is the same as 2 into alpha plus beta. This implies that this is the same as 2a. So therefore our angle A is equal to theta out of 2. That is how it comes out. That is how it comes out. So after having seen how to measure the angle of the prism, let's now turn to measurement of the minimum angle of deviation using a prism spectrometer. Remember that the angle of deviation is defined as the angle between the original direction of the light ray and the final direction of the light ray. In other words, from this diagram here, we can see that originally the light was coming from point X, from the collimator, up to point Y, we have the telescope. Always, that is where we begin from. So, incidentally, after some time, you can see that in case we place the prism in between the two, the collimator and the telescope, we have to move the telescope to a given position such that we can be able to see the slit of the collimator. In other words, if the telescope is in this position T2, then the angle between the original direction and the final direction, that is the angle of deviation. If the telescope is at T1, the angle between the two is the angle of deviation as well. So in this experiment, we want to determine the minimum, the least possible angle of deviation caused by a prism. So in this case here, what we do is basically simple as well. And the first step that we do is that we assemble the spectrometer in such a way that the prism is not in anywhere between the collimator and the telescope. So we begin by having the collimator and the telescope in a straight line. So at this point, simply take note of the angle theta naught of the prism from the turntable, from the spectrometer scale. Then, after that one has been achieved, then you replace the prism onto its turntable in such a way that the refracting angle of the prism is pointing away from the collimator direction. So once you see that, then you have to turn the telescope, like we saw in the video, you have to turn the telescope, and you do so until when the image of the slit is seen the plane of the cross wires. So once that one has been achieved, then you simply take note of the telescope position and read its position as theta 1. Now, at that point, since we are looking at the minimum angle of deviation caused by the prism, in case you remember that if this is our prism here, we have the normal, we have the incident ray, and then the refracted ray, and then the refracted ray at that point there. So the angle of deviation is the angle between these two. So we can see that in case we reduce this angle of incidence I, even the angle of deviation D also reduces. So in this case here, what we're going to do, we are, after having seen where the position θ1 is, the cross wires, the slit is seen on the cross wires of the telescope. So what we're going to do now is that we're going to turn the table in a direction such that the angle I reduces. So as we're turning the table, we do turn the telescope concurrently. We turn the two concurrently. So as you're moving the turntable, you also move the telescope such that the image of the slit is kept in the field of view, is kept in the same position as the cross wires. So as you're doing that, you'll find out that as the telescope is moving upwards, even the angle I also reduces. But time is going to come when the eye cannot reduce anymore, in that as you are reducing on the angle of incidence, the telescope goes up and then somewhere it turns. In other words, both of them are supposed to be reducing. The angle theta between the two, the angle D, is reducing as well. As the angle I reduces, the angle D also reduces. But time reaches when you increase the when you decrease the angle I further, the angle of deviation D instead increases. So what you need to do is that at that position where there is a turn of events, where the angle of deviation starts to increase abruptly, that position is what you're calling the T2. And that position will give us the angle of minimum deviation of the prism. So what you have to do is to take note of the angle θ2, and then simply get the difference between a theta and θ2. That will give us the angle of minimum deviation, like we saw in our video. So in short, this is what we do have. That the prism table is fixed and the prism is removed. The telescope stands to T0 to receive the undeviated light directly from the collimator. You take note of the telescope position as θ0. Then the prism is placed with the refracting angle pointing away. That is a very important point as well. And then the telescope is rotated to a position T1 in such a way that the direction, in such a direction that the image of the slit remains centered on the cross wires. So take note of the telescope position θ1. Then rotate the turntable so that the angle of incidence is reduced, and then rotate the telescope to keep the image of the slit on the cross wires. In this case, it means that you're turning both of them, the table and the telescope, so that the image remains on the cross wires. The image and the telescope slowly approach X, Y, in other words, the original position of the telescope. The image approximately reaches that. However, at a given position T2, a stage is reached where the image of the slit begins to move in the opposite direction. We saw this in the video. So, when it starts to move in the opposite direction, simply take note of this telescope position as θ2. As θ2. Then, the position will give the minimum deviation, and the angle between the telescope position T2 is measured from the scale of the spectrometer and is noted. This is the angle of minimum deviation. So that is how we get the angle of minimum deviation. So after having seen, we're going to be looking at some calculations. But before we do that, let's first of all look at how to determine the angle, how to determine the refractive index of a glass prism. So for a glass prism, this is what we do. Remember that from Snell's law, N1 sine I1 is equal to N2 sine I2. And remember that our angle of deviation D is given by I1 plus I2 minus the A. So for minimum deviation to occur, our I1 is equal to I2 and our R1 is equal to R2. Remember this, we discussed this some time back. So meaning that here, our D mean will simply be equal to 2I minus A. In other words, our A is equal to R1 plus R2, implying that our A is equal to R. And therefore, our angle of refraction will be simply A out of 2. Likewise, from this equation here, our angle I will be equal to D mean minus, actually plus A, then everything divided by 2. So in case we take one point, if this is our prism, we take one point, we have the angle of incidence and the angle of refraction. So this is our medium 1, this is our medium 2. Simplifying, substituting into this, we shall be simply having refracting index of air as 1 times sine of angle of incidence I is equal to refracting index of the glass times the sine of angle of incidence in the glass, which is our angle R. So making our NG subject of the formula shall have sine I over sine R. And substituting our equation is double star and star, we shall simply be having sine of D mean plus A out of 2 divided by sine of A out of 2. In other words, for us to describe an experiment of determining the refractive index of a glass prism using a spectrometer, we need to get the refracting angle of the prism and then the D minimum. So simply highlight the steps in measuring both of these two, and then finally end up with this equation. That will give us the expression of refractive index of the medium. In other words, this is what that use a spectrometer to obtain the refracting angle A of the prism, use it to obtain the angle of minimum deviation D mean as well, then finally obtain the refractive index from the expression n is equal to sine D mean plus A over 2 over sine A over 2, and that is all about determining the refractive index of the glass in form of a prism using a spectrometer. Now, note that we can determine all of these using our optical pins in the laboratory, the physics laboratory. Instead of using the spectrometer, we can design experiments using the optical pins, and you'll see this when you go back to school. I'm going to share some notes about this method of using the optical pins. You can read through and compare the two. That one is going to be for you to read through and compare. So that is all that we can say about the measurements concerning the spectrometer. About the wavelength, that is something different. We'll meet it later on. Now, other terms that we use in prisms refraction include the grazing incidence. The word grazing simply means going along the surface. Going along the surface. So if you're talking about incidence, the ray of incidence, the incident ray, it means that the incident ray is going along the surface of the prism. And according to this, this is our incident ray. It is grazing the surface. So in other words, the angle of incidence I is equal to 90 degrees. And from what we looked at some time back about critical angle total internal reflection, in case we're talking about the principle of reversibility of light moving from a denser to a less dense medium, then this angle here becomes the critical angle. Angle of incidence is the denser medium, for which the angle of refraction is 90 degrees. So since the light is coming towards, then we shall simply have this one as the grazing incidence. So we can have this this emergent ray here as grazing as well, or both of them grazing, as we're going to be seeing here. So grazing incidence simply occurs when the incident ray moving along the refracting surface pitch is refracted such that it emerges out of the prism through the refracting surface to R at any angle of emergence E. The angle of incidence is 90 degrees. Now, this one shouldn't confuse us. Just know that whenever talking about grazing incidence, the angle I is equal to 90 degrees. That's all. Then we have the grazing emergence, the ray that is coming out of the prism. It is the opposite of the other one. So the angle of emergence is equal to 90 degrees. That is grazing emergence. The word grazing simply means going along the surface. The rest of the discussions that we've been having simply applies. Snell's law, R is equal to A is equal to R plus C, and so on. So grazing emergence simply means that when a ray incident on the refracting surface PQ is refracted such that it emerges out of the prism along the refracting surface QR. In other words, the angle of emergence is 90 degrees. That is what you need to know about grazing emergence. We may not ask you about what these words here mean, but we'll need to know them. They need to be implied in the calculations. You need to be knowing them. So in both cases, you can have the grazing incidence or emergence. The light suffers a maximum deviation. Then we can also have both of them like that. That's what we just seen. That in case we have grazing incidence and grazing emergence, then we have 90 degrees on both sides. Angle of incidence, angle of emergence, 90 degrees, 90 degrees. We're going to be seeing examples concerning this. And one thing that we need to note about this is that in case we have such a scenario, in other words, grazing incidence and grazing emergence, then the limiting angle of the prism comes into play here. What is this? The limiting angle of the prism is obtained when the incident ray and the emergent ray grazes the surfaces. So that is our A. That is our A. So with this, I'm stopping here on this. Let's meet again in the next video with some examples, numerical examples, and then after we shall be doing an exercise. Please always try out those exercises to check your understanding. Whenever you answer an exercise, you can check on the hint, or you can check on the preview and then check where you went wrong, and then you correct yourself. Otherwise, thank you for watching. See you again.